Okay, Larson 3.9 differentials. We are going to actually look at using differentials to approximate things using tangent lines. Now, according to this example, we're going to find the tangent line of the function f of x equals 1 plus sine x at the point 0, 1. And then we're going to use a table to compare those y values of the tangent line with those in the interval, open interval at x equals 0. So I take the derivative of 1 plus sine x and I get cosine x. I plug in 0 and I get that the slope at 0 is 1. So then I find my equation of my tangent line, and now what I have is the tangent line and my function. Now I need to compare the values. So I put a table together, and basically you can put this in your calculator and you can put these numbers into your table to find out what the function equals, and then put those same x values to find out what your y equals. And you could see that as you get close to 0, the closer you get to 0, the more your function actually equals what the tangent line is. Okay? Now, differentials we've used where you said y equals f of x, and we take differentials which would be dy equals f prime x dx. Now if I said that the change in y is approximately equal to dy, we could then write delta y equals f prime x dx. Now we're going to compare delta y with dy. Now we're going to let y equals x squared. We're going to find what dy equals when x is 1 and dx is 0.01. And then we're going to compare this value when x is 1 and delta x is 0.1 and see how close those are. So here's your original function. And I take the differential. And I would write it like this. And now I put in 1 for x and 0.01 for dx. Now if I take this differential and plug in 0.1, I'm going to get 2 times 0.01. Alright, plug in 1. And when I multiply this out, I get dy to equal that. Let's see how close delta y is to that. Now remember, delta y is just your change in y values. So what I'm going to do, this is y2 minus y1. So I plug in 1 plus 0.01 minus f of 1. And if I put this into my original function, I'm going to get 1.01 squared, because remember f of x is x squared, minus 1 squared, and this is my value. So as you can see, when we're dealing with small changes in delta x, delta y and dy is about equal. Now we're going to talk about error propagation when we're looking at finding the estimated error. Now remember, f of x plus delta x, this is an exact value, and delta x is what we measure. It's the error in measurement. This x is the measured value, and this is the propagated error. So if I have the radius of a ball bearing is measured to be 0.07 inches, if the measurement is correct to within 0.01 inch, estimate the propagated error in the volume. Here's the volume of a ball. Here's my measured r value. I take the differential dv, which we've done before, and I simplified it. Here's my measured value, and this is my error, not my error, but this is where the radius can change 0.01 plus or minus in either direction. And I plug that in, and this is what my error is going to be, that my volume can vary between plus or minus 0.06158 inches cubed. Now, how do we calculate differentials? Remember, this is f of x plus delta x is approximately equal to f of x plus whatever my change is in dy, which is approximately equal to that. So now we're going to approximate function values. We wouldn't do this ordinarily. We just plug it into our calculator. F of x equals the square root of x, which again is x to the 1/2. And I take the derivative, and I get 1/2 x to the negative 1/2 dx. Now, remember, I'm saying plus a small change. So, f of x plus delta x is approximately equal to f of x plus my change f prime x dx. So f of x is the square root of x. plus my derivative, dx. And now I'm going to choose 16 because we're looking at 16.5, so the perfect square nearest that is 16. My dx is 0.05, and I plug it in, and I will get approximately 4.0625.